Good morning, good afternoon, good evening, everyone. I'm going to want to talk to you today about our progress in automating our efforts to make theoretical chemical kinetics estimates. Our main goal in this project ultimately is to be able to generate fully theoretical mechanisms with thermal properties and transport and rate constants for everything. Today I'm going to focus on a demonstration that we did recently for exploring the initial stages of pyrolysis. And this project and this particular talk is really the primary effort of three people: Sarah Elliott, Kevin Moore, and Andreas Copan, who have been the lead programmers in everything we do. And this builds on earlier work from Murat Kec, as well as some others. And this project really has a very long sort of history. Started as my dream to try and calculate a full mechanism from first principles theory calculations. It started when I was at Sandia, and then I was trying to do things by hand. And the first question I was asking myself, can I do this for methane? Well, that turned out to be too much to do by hand. I started thinking about the idea of automating things, and we tried that a little bit when I first moved to Argonne, but for various reasons it didn't proceed very far. Then about 5 years ago, Carlo Cavallotti came to visit us, and he really took up the idea and really got us going. And the first result of that was a procedure for automatically predicting the rate coefficient starting from the Z matrix for your set of reactants. And that was my initial aim, and Carlo met that so well, we greatly expanded our goal now to this one where we're thinking about generating a whole mechanism. And here I've just listed two sample mechanisms that give us an idea of the size of the problem. We have to look at 5,000 reactions if we're looking at a heptane, or 12,000 reactions if we're looking at a combination of isooctane and isododecane, and we're trying to reproduce literature mechanisms. Obviously, that's a very large problem. Trying to meet that means that we're going to have to have codes that are procedures for doing this that are fully automated, and furthermore that have very few errors, and so that's been a primary focus of what we do. Qualitatively, we have clearly demonstrated 90% or greater accuracy, probably about 95%. It's a little bit hard to tell as you fix errors. You don't know how many of them are fully good, but probably about 95% is what we suspect is our accuracy. With that, you still have a fair number of problems, though. So key question is that people might be asking, that anybody might ask, is can you really predict that many rate coefficients? And can you do it with sufficient accuracy? And I'm going to try and demonstrate that a little bit, as I said, for initial stages of pyrolysis in a series of alkanes, alcohols, and aldehydes with up to 4 heavy atoms. In doing that, we're looking at the abstractions to make the fuel radicals, and then the beta scission of those fuel radicals to go on to other products. And it's just a good demonstration of a particular aspect of what goes on in mechanism development. Of course, full mechanisms have a lot more classes than that, but this is the stage we're at a year ago. I'll close with a little bit of a statement of more of a demonstration of a full mechanism. So for now, though, we're looking at 70 species and about 360 reactions, 160 or so channels. And just thinking about this ability, you can already see sort of obvious utilities for this sort of thing. If you can generate this many rates, it makes it very easy to calibrate different electronic structure, different transition state theory methods, and figure out what their accuracy is by comparison with appropriate experimental or other data. We also obviously use this then to start generating rate rules, because we can do things across a whole series of species and think about how small chemical changes change things. Of course, one solution to the problem of how many reactions there are is to not do all of them, but rather do the ones that are most sensitive. But for now, our goal is sort of more simple, just try and generate the whole set, just to see whether that's a feasible possibility. So the whole project is about automating things. I want to have as little human intervention as possible. Of course, that's not zero, but we're already at the point where at least 2, probably 3 orders of magnitude more rates that I can generate with this procedure than what I can do by hand. So what do we have to do that? We have to have a way to connect from the species labels that people would give in a chem mechanism file and turn that into an actual chemical description. And there's been, in addressing this question, it's been a real eye-opener for me as I learned about chemical informatics. I was really ignorant about the whole field. And there's some great work in there. There's sort of two standard toolkits are OpenBabel and RDKit. There's probably a whole bunch of others. But these toolkits allow you to connect from chemical identifiers, thing called SMILES or INCHIs, directly into a 3D structure. And that's the key starting point that we need to be able to connect to chemistry. And then once we have a real 3D structure, we can start to try and figure out, if we're given two reactants and two products, what is the reaction that goes on. And in there you have to implement graph theory sorts of things. You have to ask yourself what bonds are formed and broken. And we've got a nice core that does all this for us now. It's written largely by Andreas Copan. And those first two phases of this project, there's a lot of analogies with what's going on in RMG, for example, and other automated kinetics procedures. The thing that we really started dealing with on our own was thinking about how to store and create files and how to make sure we're reusing electronic structure. Electronic structure is a very time-consuming task, and so we want to make sure we're reusing things as much as possible. Then the real center effort of the whole code involves a coupling of all sorts of disparate codes. We want to be able to do just thousands, tens of thousands, hundreds of thousands of ab initio electronic structure theory calculations. Electronic structure theory is a very complicated task, and so we use commercial codes for that, and we've tried to make it so it's easy to switch from one commercial code to another and just have a very specific set of routines that have to be written for a given code. Oddly enough, although electronic structure theory has had good codes for 40, 50 years, they haven't standardized any of their I/O, and so we have to do that all separately for different codes. The rate constant evaluations we do, it's all based on a nice code that Yuri Georgievskii wrote for us to implement the master equation and include transition state theory, microscopic rate calculations, directly from structural information from electronic structure theory. Then we've also got trajectory and transport information and codes from Aaron Jasper, and then we've been writing our own fitting and rate comparison codes. Of course, the first step of the analysis is to figure out what kind of transition state theory you have, and then efficiently and reliably find that. We have a different twist on that from most other people, but I don't have time to talk about how we're doing it. We have to evaluate the stationary point properties, symmetry numbers, and then it's all wrapped around in some big workflow management and automated error recovery. I don't have time here to tell you too much about exactly how we do this, but this is just an illustration of the basic idea. The basic idea is we just have an input mechanism and then a list of transition state theory options and electronic structure options. And then and you tell the code what you want to do with those, and then it will generate an output mechanism. And the kind of things that you're telling it what you're going to do about it are in that box in the top right, which is telling us about conformation. Do you want conformational sampling? Do you want to do geometry optimization? Find your gradients and Hessians, single point energies, symmetry factor determinations, IRC evaluations to test your transition state, hindered rotor scans, and just generic transition state searching. So we have drivers that will call any one of these according to the desires of the input commands, and then extract all that information and generate mechanisms. So now what are we doing that? Well, we took that and we made these potential servers. Here's the sample, first one, C4H9. It's a pretty simple potential, 2 minima and a number of product channels, but we're able to automatically generate that potential, solve the master equation, get our temperature and pressure dependent rate constants, fit them to P-log or Chebyshev, or if it was a single well, to a TROA format. And we've got 4 different methods we use here. We just wanted to show that we can do a variety of methods, and from relatively cost efficient to fairly high accuracy, and we did simple RHO and 1D hindered rotors as representative. A slightly more complicated potential, C3H701. Here we have literature values that we compare with. Our predictions agree with those to within a half a kcal. Probably ours are even slightly better than the prior published literature values, simply because we've got better basis sets in both the high level energy and a better DFT method. Prove that we can do that. And the most complicated potential we looked at in this project probably was the C4H901, and just as an example of how complex things can get. It looks like there's 5 minima on this potential. One fun thing that we can do with the MES code is look at the stability of the radicals. Beyond a certain temperature, they'll dissociate faster than they'll stabilize, and this shows how that varies with temperature and pressure for the whole series of radicals we looked at. A more important thing to look at is how well are we doing in terms of predicting the rate constants, and this is sort of the same thing you would do with any kind of rate calculation, right? Just generate the rates and see how it compares with the literature data. And there's often ambiguities in the literature data, so it's not always exactly clear. But the qualitative conclusion you can come to after looking through the results I'm going to scan over here is that we have about at least a factor of 2 or better prediction for every case. That first slide was for methane, small alkanes, and here we have also the methyl abstraction and also branching propane. Here we have for OH plus methane and ethane. A little bit more ambiguity maybe in the experimental data, a little bit of a deviation at the highest temperature. But again, everything's within a factor of 2, except perhaps for this L1 method. The basis sets aren't quite good enough, and so there you get more like a factor of 3 sorts of uncertainties, or perhaps even a little larger. The most complicated thing starts to come when you deal with the alcohols. Here's an alcohol plus H, and we have alcohol plus OHs. And here now we have to start dealing with hydrogen bonding interactions, and variational things start to become more important, and so our errors have increased somewhat. So clearly we're able to produce rates that are at the right sorts, that have pretty good accuracy, better than factor of 2, and are useful for mechanism. So then the question you might ask is what's next? And here I'm saying future is now, because it's already a year, and since we submitted this paper, we've done quite a bit more. For the project that we're doing this with, we had to do some mechanism development for isooctane and dodecane. And here you see we're treating 1,400 species thermochemistry and 3,000 reactions. And we've expanded a number of reaction classes. We're really doing essentially all of the classes in a mechanism. Not quite all, but almost all. Migration, elimination, insertion, substitution. We're now able to treat the whole RO2-QOH chemistry. We've generated new schemes for trying to get high-level energy. So now we're doing things with as many as 16 heavy atoms. We've got high-level energies from low-level calculations and reference fragment benchmarks. We've got anharmonicity corrections by various scaling procedures. We've got some corrections for hindered rotors and scaling, and then we've got procedures now also for automatically comparing rate constants from different mechanisms, one we create versus one in literature, for example. I close by just acknowledging our different funding sources. We've been fortunate to have a good source of funding over these last 4 years from the Exascale Computing Project. Kevin Moore, one of the primary workers on this, has also been supported by the U.S. Army Research Office. Sarah Elliott had the fortune of having a DOE Computational Sciences Graduate Fellowship and is now a postdoc in the group and working again through Exascale Computing Project funding. And I've been funded through both the ECP and also through our main DOE core program, and we've had some computing support from the LCRC. Thank you for your attention.